Hello, welcome to the first lecture on organic chemistry, or really the first supplemental lecture to help us get a few of the organic chemistry facts down that we're going to need to be really successful in this part of the class. So organic chemistry is really defined as molecular compounds that contain carbon and hydrogen. So sometimes there'll be other atoms too, like oxygen, nitrogen, sulfur, but the main thing is that the carbon and hydrogen is the main core part of the molecule. So organic chemistry really is about compounds that are mainly consist of carbon and hydrogen. In order to really get into organic chemistry and start looking at understanding the compounds, I want to first do some reviewing of our basic chemistry facts about carbon atoms. So remember, based on its position on the periodic table, carbon has 4 valence electrons. So when we draw Lewis structures of a carbon atom, a Lewis structure, Lewis dot structure, you can see here's our carbon atom, and we put 4 dots around the carbon atom. Those are electrons that are available to form bonds. Because carbon has 4 valence electrons, you'll remember that that means that it wants to form 4 bonds in order to be happy. So in order for that carbon atom to get its octet, it needs to form 4 bonds, pair up those electrons so it has 8 electrons around it. That'll make it stable. So carbon atoms in organic chemistry will always have 4 bonds. In this class, that's crucial. If you look at a carbon atom and it has 3 bonds, something's wrong. If you look at it and it has 5 bonds, something's wrong. Every time you look at your carbon atom, it should have 4 bonds. Okay, so let's just look at our simplest example here. Methane is our smallest organic compound because it just has 1 carbon atom and 4 hydrogen atoms. So I'm sure we worked on this Lewis structure back when we did Lewis structures, but as sort of a reminder here, there's our carbon atom with our 4 dots around it. Each hydrogen atom has 1 dot, so we can share those electrons. And that results in there being 8 total electrons around that carbon atom. If we have 8 electrons around that carbon atom, we can display those also as a bond here. We get a stable compound. So 2, 4, 6, 8 electrons around that carbon atom, and also notice that there are 4 bonds around this carbon atom. In organic chemistry, when we are showing every single one of the bonds in the compound, in the organic compound, we call that the expanded structural formula. Okay, so that's the expanded structural formula. We're showing every single bond in the compound. So what I'd like us to do right now as an exercise is draw propane, which is C3H8. It's a 3-carbon chain. And we're going to draw it using the expanded structural formula. Okay, so what I'm going to do is I'm going to start by drawing 3 carbon atoms in a chain. So there's my 3 carbon atoms, C3, 1, 2, 3. 3 carbon atoms in a chain. Now I'm going to add my hydrogen atoms on. And all we need to do is to keep in mind that each carbon atom has to have 4 bonds. If the carbon atom has to have 4 bonds, how many is this one missing right here? It's missing 3. I'm going to add in 3 bonds there. So I'm going to add those in. Those are going to be my hydrogen atoms. H, H, H. Look at this carbon atom right here. It's already got 2 bonds, so it needs 2 more to be happy. 1, 2, H, H. And this one only has 1 bond right now, so I'm going to add on 3 more H, H, H. Okay, so now we've got our 3 carbon chain, and let's count 1, 2, 3, 4, 5, 6, 7, 8. 8 hydrogens. So we've got our C3H8. So as long as we're focusing on getting these carbon atoms having 4 bonds, we're always going to be able to draw the compound that's given to us as far as the straight chain hydrocarbons that we're talking about. The next thing I want to talk about are the types of ways that we represent these compounds. So here's our propane molecule again. It's C3H8. And the way that we drew it last time was the expanded structural formula. In other words, we showed every single bond in this molecule. Sometimes it's convenient to skip showing every single bond, particularly with the carbon-hydrogen bonds, because those tend to be pretty non-reactive and not that exciting. So lots of times what we do is we have what we call a condensed structural formula. So notice now, this is the condensed structural formula of C3H8. Both of these are representations of the same molecule. But notice now here, instead of showing those carbon-hydrogen bonds, there's 3 hydrogen bonds up here in this structure, I just wrote it as CH3. Now, I wrote it like this because we always write the carbon atom first and the hydrogen second, or most of the time we do that. This bond then is not bonded to the hydrogen atoms here. This bond is actually the carbon-carbon bond. So this bond right here, this carbon-carbon bond, is still being shown right there. So I just have to know that those 3 hydrogen atoms are bonded to this carbon and not bonded to that bond right there that's shown there. Same thing here, the CH2 group is this group right here in the middle, the CH2 group, right there. And on the end we have a CH3 group. So that's a condensed structural formula. And honestly, this is probably what I'll use most in class and in the lectures are the condensed structural formula. In the condensed structural formula, the CH bonds, for the most part, are not shown. Now, we will get some exceptions of that when we start talking about functional groups, particularly aldehydes. But right now, in regular organic compounds, that CH bond is not shown. We condense that down. That's what makes it the condensed structural formula. The CC bonds, however, are still drawn. The last type of compound that we have is called the skeletal formula. And the skeletal formula is the absolute simplest formula. The skeletal formula only shows the carbon-carbon bonds. Doesn't show any atoms, doesn't show our carbon and hydrogen atoms, that is. So it only shows the carbon-carbon bond. So again here we've got our CH3, CH2, CH3. There's my condensed structural formula. This bond right here is shown right there. This bond right here is shown right there. So those are the 2 carbon-carbon bonds that are shown. Everything else is not shown. We're not showing the element names, and we're not showing the hydrogen atoms at all. So when we see a skeletal formula, we have to know that on every end right there and every point right there is a carbon atom. So those 3 circles that I drew right there are carbon atoms. Now this circle on the end is a carbon atom with just 1 carbon-carbon bond, so we know it has to have 3 hydrogens around it. This one right here that I circled is a carbon atom that has 2 carbon-carbon bonds, so we know there must be 2 hydrogen atoms off of this one. Same thing here, there's got to be 3 off of that. So the skeletal formula telling us the same information. Each end and point is a carbon atom. We're just leaving off actually drawing the element symbols, the carbon and hydrogen. And that's our skeletal formula. Okay, before we get started on doing more work with understanding how to write the different formulas, I want to cover the naming of very simple alkanes. And this is going to be key because this is going to build our foundation for all of the naming of organic chemistry. So we have to make sure we get this down really well. Once we talk about this a little bit, we'll work some examples on drawing those different kinds of formulas. Okay? So we're going to start with naming simple alkanes. So we have to do a definition here. We have to define exactly what an alkane is. An alkane is an organic compound that contains carbon and hydrogen only. So only carbon and hydrogen, and only has carbon-carbon single bonds. So these are our simplest organic compounds. Purely carbon and hydrogen, what we call hydrocarbons, because they have carbon and hydrogen in them. It's an alkane. And alkane specifically means carbon-carbon single bonds. Okay? We need to memorize our alkanes 1 through 10. 1 carbon atom through 10 carbon atoms long. Because this is going to be our foundation for naming every single organic compound. So we need to know how to do this. Okay, so we've already looked at the simplest carbon organic compound, methane. Methane has 1 carbon atom. Now the name is made of 2 parts. Meth is the first part. METH is the organic abbreviation for 1 carbon atom. And then ane is the abbreviation for an alkane. So when I put these 2 things together to say methane, I know I'm talking about a 1 carbon alkane. So every organic compound that we need to worry about, 1 through 10, has a name. So ethane is our 2-carbon chain. So we said that now that's ethane is made up of ETH is the root part. That means 2 carbon atoms. And then we're adding on the ane because I'm talking about an alkane. Okay. So I'm just going to show you all of these right now, and we'll refer to this if we need to. So here are our 10 that we need to memorize to tell us how many carbon atoms there are in the organic compound. So for example, we were working before on the page propane. Propane, the prop part means that there are 3 carbon atoms, and the ane part means that it was an alkane. Okay. So meth, eth, prop, bute, those are, I think, some of the harder ones to remember because they're not directly related to more of the traditional sort of Greek numbering system. When we get up to 5, then it does follow that. So pent for pentagram, that's 5-sided symbol. So pent is 5. Hex for hexagram or hexagon is 6. Hept is 7. Oct is 8, like octane, like we put in our car for gas. 9 is known, N-O-N, so nonane. And then 10 is decane, D-E-C, dec. So we need to know those 10 prefixes and how they work. So for example, if I want to know what compound is that's butane, this, I look at the front and I say, okay, butane means that there are 4 carbon atoms. The ane part means that this is an alkane. Alkane means carbon and hydrogen only with carbon-carbon single bonds only. So if I want to draw the structure of butane based on the name here, I'm going to draw my 4 carbon atoms in a chain, all with single bonds. 1, 2, 3, 4 carbon atoms, all with single bonds. Then if I want to put my hydrogens around, again, we base it on this rule that each carbon atom has to have 4 bonds. 1, 2, 3. 1, 2, 1, 2, 1, 2, 3. So we can put our hydrogen atoms around to fill them in so that each carbon atom has 4 bonds. So there is the structure, the expanded structural formula of butane based on its name. If we wanted to know the exact formula, we could write that down now based off of what we just drew. There are 4 carbons, 3, 6, 7, 8, 9, 10 hydrogens. So C4H10 is the correct formula of butane. Now that we've covered the very basics on naming our straight chain alkanes, I want to just do a couple practice problems and point out something that's crucially important for understanding our organic compounds as we go along. Okay, so we're going to start by doing some exercises. We're going to name the following alkanes. Okay, so I'm going to look at this compound here. This is the condensed formula, because see the carbon hydrogens are condensed down. There's 1, 2, 3, 4, 5 carbon atoms. So if you don't remember, let's just refer to this really fast. 5 carbon atoms is, the prefix is pent. And since this is a regular alkane, all carbon-carbon single bonds, this is going to be called pentane. So that will be the name of that alkane. 5 carbons. Now we can display this differently, so we should be able to identify and name any of the alkanes that are drawn with the different ways of drawing them. Here's a skeletal formula. So again, we can count bonds, or I like to prefer to count the ends and the middles. So I'm going to circle each one. Here we've got 1, 2, 3, 4, 5. Each of those positions there is a carbon atom, and they're all single bonds. So since there's 1, 2, 3, 4, 5, this is also pentane. So we need to be able to recognize and name both those types of formulas, the condensed and the skeletal formulas. Okay. Now, the crucial point, when I look at compounds written like this, It doesn't matter the arrangement of the atoms. What is the most important thing is that there's a chain that you can trace with your pen. So when I go to name this compound, it doesn't matter at all that this is bent like this, that this is in sort of a 7 shape here or a corner. Doesn't matter. Still just try to count them all in a straight line as if I can draw my pen through them. 1, 2, 3, 4, 5 carbon atoms. So the key here is I can still find that straight chain by drawing a single line through it. Since there are 5 carbon atoms, all single bonds, this is also pentane. So that's a crucial thing and something that's really easy to miss. And this is because there's free rotation around these bonds. So these molecules in actuality can twist and turn and can kind of fold up. They're not always in a perfect straight line. So sometimes we draw them not in a straight line. That might be important for what we're displaying. Okay? Here's a skeletal formula again. 1, 2, 3, 4, 5. Pentane. Doesn't matter what shape they're in. 5 carbon atoms all in a line. If you can draw a straight line through them, they're all in a line. Okay? Doesn't matter how complicated we get. Here's 1, 2, 3, 4, 5. So this will also be pentane. Now, and if you're not sure if they're all part of the same chain or not, and we're going to see different examples later on of branched hydrocarbons, there's sort of 2 tests. What you do is you can circle them. If you can circle it without picking up your pen, make a complete circle without any molecule coming off of here, and we'll see more complicated examples going on. We know they're all in a straight chain. Or if you can draw your line through the carbon atoms without picking them up. That's the other test. So these are all in a straight chain. Even though I didn't draw it straight, I would still call this a straight chain. 1, 2, 3, 4, 5 carbon atoms. Same thing for the skeletal formula here. 1, 2, 3, 4, 5. Also pentane. So if they're all in a line, different ways of representing the exact same thing, pentane. As the last exercise on this introduction to organic chemistry and specifically naming, let's do this last exercise where we draw the expanded, condensed, and skeletal formulas of hexane. Okay, so we're going to focus on drawing that of hexane. So again, we need to look to see what does hexane mean when it comes to organic. If you don't remember, let me find my cheat sheet here. Hexane is a 6 carbon chain. So hex means 6. And the ane means it's an alkane. So this is 6 carbon alkane. Remember, an alkane is carbon-carbon single bonds. So I'm going to start with the expanded formula. 1, 2, 3, 4, 5, 6 carbon atoms. 1, 2, 3, 4, 5, 6. Now I have to fill in the hydrogens, so each end carbon is going to get 3 hydrogen atoms. 1, 2, 3, 1, 2, 3. Because now all of those 2 carbon atoms have 4 bonds. Every single carbon in the middle already has 2 bonds, so each one of these is going to get 2 more hydrogens. So we put that all in like that. So there is the correct structural formula of hexane. If they would want to check, we could now write to see what the formula is. C6H 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. H14. That's the correct formula for hexane. Condensed formula is just going to condense the hydrogens down into the carbon. So this will be CH3, CH2, 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 CH3. 1, 2, 3, 4, 5, 6. So condensed down, not showing the carbon-hydrogen bonds. Finally, the structure, the drawing with the least amount of detail is the skeletal. When I put my pen down, I count that as 1 because I know that's an N. So there's 1, 2, 3, 4, 5, 6. And we always alternate. It doesn't matter if I start up or down. This one I started down and I went up. Same thing if I went like that. 1, 2, 3, 4, 5, 6. Same thing. Both of these are hexane. Doesn't matter. And if you're unsure, just double check the count. 1, 2, 3, 4, 5, 6. Okay. So that's our 6-carbon chain in the skeletal formula. So we've got expanded, condensed, skeletal formulas. And those will be 3 different representations that we'll be using depending on what the application is. All right, so our next lecture will get into branched hydrocarbons, and that will be taking this up to another level of difficulty, but we've got the introduction done now, which is what we needed. Great, see you next time.